recording. All right, so I need my pen. So what are we going to talk about this week? So I guess you can see on the board, we're going to be drawing pictures a lot. And so we're on to the last two sections of our textbook, which are 9.9 and 9.10, and they're phase portraits and nonlinear systems. So let's talk about then these two sections. Draw. All right, so 9.9 is going to be phase portraits for linear systems, or phase plane portraits for linear systems. So what we've been dealing with recently is that we've been dealing with, right, x prime is equal to ax. And a usually for us has been constant coefficient, which is good. But what we can do instead is, right, we can write more generally, right, x can equal like some function of x and y, or x prime can equal some function of x and y, and then y prime can equal some other function, let's call it g of x and y as well, right? And these two are like the same things for x prime is equal to ax. We're just writing them out. This one is like row by row. The bottom one's like row by row, and the top one is like by a matrix. So for a linear system, we have constant coefficients in A, right? So the elements of A are all in, so A is in M2 R, okay? Or I guess we can make it complex numbers. We don't have to deal with real numbers, so M2C. But the idea is that A has constant coefficients. And so what we talk about in phase planes is that we usually talk about 2 by 2 invertible matrices. Because if we talk about non-invertible matrices, you're going to see that we're going to create this table that actually doesn't allow us to deal with non-invertible matrices. And the last thing we want to talk about then is the equilibrium points, which are defined as the following. They're points x and y such that f of xy is equal to g of xy, which is equal to 0, right? So set notation is back, but our equilibrium points are just all of our points where if we look at x prime, that's 0, and if we look at y prime, that's also 0. Okay? So for linear systems, we only have one equilibrium point, and can anyone guess what that equilibrium point is going to be? 0, 0, right? It's going to be the origin, because if you plug in 0, 0, right, if you think of it, you plug in 0, 0 into x prime equals ax, that's going to be an equilibrium point. So for linear systems, 0, 0 is the only equilibrium point. Okay? So how do we determine the behavior of systems of equations around these equilibrium points? So behavior of systems around equilibrium points. All right, and here we have to look at the eigenvalues and eigenvectors. And more importantly, just the eigenvalues. So I guess on somewhere in your notes where you can refer back to, you're going to have this table that we're just going to refer to like over and over today. So you're going to have your eigenvalues, right? And then we want to characterize the type of equilibrium point given those eigenvalues. So what do we have? Okay, so for eigenvalues, what cases can we have? We can have real and both greater than 0. Or let's do less than 0. Real and both less than 0. So what kind of equilibrium point are we going to have? So what kind of equilibrium point do we have if we have two real eigenvalues and both are less than 0? we're going to get a stable node. Okay. What about if we have two real and both greater than 0? Well, since the eigenvalues are greater than 0, we're actually going to get an unstable node. Okay. How about real? Or let's see, real and opposite sign. Right, so we have real eigenvalues, but one's positive, one's negative. Now you get a saddle point. All right, pure imaginary. So a plus bi, but a is 0. We get a stable center. Complex, real part less than 0. Right, so you have a plus bi, but a is negative. You're going to get a stable spiral. And then complex, real part greater than 0, you're going to get an unstable spiral. Okay, and notice that in none of these cases, we consider 0 being an eigenvalue, right? So that's why we deal with invertible matrices, because otherwise, if 0 is an eigenvalue, you get a lot of problems. Okay, and this table is actually like universally hated by like all the professors that teach this class because apparently it's wrong. I don't exactly know why it's wrong, but from I think it's wrong because it's like missing like a few cases. So it like under some specific eigenvalues, there might be like some subcases that just aren't considered by the book because of the matrices that we deal with in this class. So it is what it is. Okay, so let's look at then examples of sketching these systems and like in general just figuring out what the hell is going on. Okay, so is there a question? Okay. So let's look at examples. Let's say we have number 1, x prime is equal to 9, negative 4, 15, negative 7, x. Okay, so the term of a naught minus lambda I, 9 minus lambda, negative 4, 15, negative 7 minus lambda, and you'll get lambda squared minus 2 lambda minus 3. So that's lambda minus 3, lambda plus 1, and lambda is equal to negative 1 and positive 3. Okay, I'll take it. Thank you. All right, so we have two real eigenvalues. All right, so if you have real eigenvalues, we want to find the eigenvectors. If you have imaginary eigenvalues, just then we'll see what happens there. But so for real eigenvalues, let's find the eigenvectors. Lambda equals negative 1. Got 10, negative 4, 15, and negative 6. Right, and so the eigenvector is 2, 5. For lambda equals 3, we'll get 6, negative 4, 15, negative 9, and your eigenvector here will be 2, 3. Yeah, it might be. Yeah, I think so. Yeah. Thank you. Yeah, actually, I have just something completely wrong written in my notes here. So, no, but yeah, that's negative 10. All right. So, okay, so now what? So now you find your eigenvalues, you have your eigenvectors. So now we can actually draw the picture to the system. All right. So we want to draw a picture of our system. And again, we deal with two by two matrices because we can actually draw it in the xy plane. Okay. And so now what do we do? Well, here's our equilibrium point. Right, it's 0, 0 at the center. And what we want to do is we want to draw eigenvectors going out of that equilibrium point. So here I'll have like 2, 5, which is a kind of steep eigenvector, right? And then I'll have 2, 3, which is somewhat less steep. Okay. So now what? So now, right, notice how I didn't commit to like any direction of the arrows of the eigenvectors are going. So that's the next part, is we need to figure out what directions are these eigenvectors going in. So, so what direction is, let's say, the green eigenvector, which is 2, 5, going into? Well, how can we figure that out? We can pick a point on 2, 5, and then we can look at, right, we can look at what the derivative is, right? So if we pick, right, so what's a point on this eigenvector in the direction of 2, 5? 2, 5, exactly, right? It goes from the origin and it goes in 2, 5. So on 2, 5, right, what's going on? Well, x prime is equal to, so my original matrix is 9, negative 4, 15, negative 7 times 2, 5, right? And we see that this is equal to negative 2, 30 minus 35, negative 5. Well, we expected a scalar multiple of the eigenvector back because that's what eigenvectors and eigenvalues are, right? And here, essentially, you see that, oh, hey, AV equals lambda V, so we would just multiply it by negative 1. So at this point, we're at negative 2, 5. So it means at the point 2, 5, we're going in the negative direction, right? So it means we're going towards the origin here, right? And the same thing if we're on the other side of the origin. If you plug in this point down here, your eigenvalue was negative 1, so you're actually going then towards the origin again. So that's the direction our green eigenvector is going in. All right. So now what about the other one, lambda equals 3? Well, for lambda equals 3, you realize that, okay, if I plug in the point 2, 3, I'm just going to get scaled by 3, right? Which means the derivative at 2, 3 is going to be positive, is going to be 6, 9, right? So that means on the orange vector, I'm going to be headed in the positive direction, right? So on 2, 3, right, x prime equals ax, right, and x prime is equal to this guy times 2, 3, but that's just equal to lambda v, or lambda x, which is 6, 9. All right, and so that's going out in the positive direction. And so down here, it's also going out in the positive direction. Okay, so what's really going on with the behavior of a system? Well, if you choose a point out in space, right, let's say this point, what's going to happen is it's going to follow the eigenvector. It's going to approach the eigenvector going towards the origin. But as we get closer towards the origin, the effect of this orange eigenvector going away from the origin is going to pull it away. All right? So in essence, right, we go near, but we never actually hit the origin, and then we start, so this is actually asymptotic. So we actually start asymptoting towards that eigenvector there. Okay? The same thing, if we pick a point between these two eigenvectors, we'll start off headed towards the origin, but then at some point, we're going to be forced to turn around and go the other way. And then if we go up, start from up here, same thing. We asymptote towards the origin, and then we asymptote towards the other eigenvector. And then lastly, if we pick a point here, right, we come down, and then we go back away. All right, and so these are the portraits that you have to draw for these kinds of linear systems. So another disclaimer is that, like, I've actually never seen these on an exam before. Well, actually, Turk likes to put them on the exam. But, so they're very rarely on the exams because, like, this isn't a drawing class. And if you can tell, like, I can't draw. So it's really hard sometimes just to like figure out what the hell is going on in your picture. But McGrath never told me if he never like committed to like not putting these on the exam. So I'm just trying to cover my ass here and showing you guys how to draw these. Okay. Any questions about this saddle point? And so we can see why it's a saddle point, because everything not on an eigenvector is actually not going to go to that equilibrium point, right? Everything's actually just going to move away. Okay. So now let's consider some other matrix. Let's say the matrix is equal to, so x prime is equal to 0, negative 1, 1, 0. Actually, 0, positive 1, negative 1, 0. Doesn't actually matter. So x prime is equal to that times x. All right. Lambda's plus or minus I. This is a really easy matrix to find the eigenvalues from, so we're not going to do it. And then, all right, so we have lambda equals plus or minus I. And if you remember your table, right, what kind of behavior is at this point? Yeah, stable center. All right, so what does a stable center look like? So all stable centers look the same. They're going to be like circles or ellipses around the equilibrium point. All right, and it doesn't actually matter. Like, I don't think we care that you know if this is an ellipse or a circle. Anyhow, so we're going to get like, so this is what the behavior looks like around the equilibrium point. What we do care about, however, is what direction these circles go in. Okay? So how can we figure out what directions these circles are going in? Or ellipses? I think they're circles. Yeah, so plug in a point, right? So if we plug in a point, we can evaluate the derivative at that point. But now here's like another question: at what point do we plug in? Right? And so for these kinds of problems, the easiest point to plug in probably is going to be somewhere along the x-axis or the y-axis. Right? And we can say that, okay, let's just pretend that this point is 1, 0, because we don't actually care about like what line we're drawing, but assume that one of these circles runs through 1, 0. Right? So assume that like plug in 1, 0, right? You get x prime is equal to 0, 1, negative 1, 0 times 1, 0. That's just taking the first column of that matrix. Bless you. Okay, so at 1, 0, we're going in the 0, negative 1 direction, right? So come out over here. Let's say this purple point on the x-axis is 1, 0. Right, we're going in the 0, negative 1 direction, which means the tangent vector to this point is going like this, right? Going straight down, 0, negative 1. All right, if the tangent vector is going straight down, that means my circle has to be rotating clockwise, right? Because now it's getting pushed clockwise by that tangent vector. And if you actually plugged in 0, 1 as your point, you would have found that your tangent vector goes that way. So indeed, we're spinning clockwise. So that's what the stable center looks like. Okay. So no, I'm not going to get to every single drawing of each equilibrium point, but your book does that. So. So I think I have a video where I talk about what a stable spiral looks like. And a spiral looks like exactly what you think it does. It goes from the equilibrium point and just like spirals out like that. Okay, any questions on this? So notice we can't find like the eigenvectors, because like what does an imaginary valued eigenvector do for us? Absolutely nothing, because we can't graph it in the 2D plane. Okay? Number 3. So now let's say x prime is equal to 3, 1, 1, 3 times x. All right, and again, I'll just give you the eigenvalues. They're 2 and 4. Okay, so now I have two positive real eigenvalues. So what does that tell me about my system? What kind of system is this? Or what is the behavior of that point? Yeah, it's an unstable node. Okay, so what does an unstable node look like? Well, so now we need to find our eigenvalues, right? Or eigenvectors. So lambda equals 2, you get 1, 1, 1, 1. And so v is equal to 1, negative 1. And then at lambda equals 4, you'll get negative 1, 1, 1, negative 1. And so v is equal to 1, 1. Okay, and now let's draw the photo, or draw the picture. Draw the photo. Draw the picture. There you go. Okay, two eigenvectors are 1, 1, and 1, negative 1. So they're going to be 45-degree lines from the origin. Somewhere like this. Shouldn't have. Oh, well. It's fine. Don't want the arrows. Right? And now we need to figure out what direction we're going in. So notice if I pick 1, 1, right? If I pick if I pick the point 1, 1 here, which direction am I going to be going? So we should be going out, right? And that's because the eigenvalue associated with 1, 1 is positive, right? So we're going further away. So we're going to 4 in the 4, 4 direction. So over here, we're actually speeding out that way, right? And again, one way you can check is you can actually just plug in 3, 1, 1, 3 times 1, 1 is equal to 4, 4, which we should have expected from the eigenvalue and the eigenvector, right? So that means down here, we're going the negative direction in the other way, right? And if I plug in 1, negative 1, so 1, negative 1 is right here, right? I'm just going to get 2 times 1, negative 1, so 2, negative 2, which means I'm going to be headed out away from the origin as well. Okay, so all these eigenvectors are going away from the origin. But here's the question: in which direction are all these lines going to approach eventually? Like which eigenvector? Why 1, 1? Yeah, the eigenvalue is larger, right? So if you think about what the system looks like, you have c1 e to the something t plus c2 e to the something t, right? So as t gets bigger, the influence of the 4 is going to be larger than the influence of the 2, right? So we're going to start at the origin, but everything is just going to approach the 1, 1 eigenvector. So it's going to look something like this. So you start at the origin, right? And then some of them are just going to start shooting up right away towards the 1, 1. But some of them might, stick around for a little bit and then start shooting up. And then some of them might stick around for a really long time and then start heading up. Okay? And then it's going to be the same thing on the other side. So you're going to have some of them just immediately start heading straight up, and then some of them, sticking around a little bit before going in the direction of negative 1, negative 1. Okay, and so that's an unstable node. Any questions about these? All right, again, just find your eigenvectors if you need to, and just plug in points to find derivatives to find directions of where things are going. Okay, so that's linear systems. Let's talk about nonlinear systems now. So this is what Professor McGrath's going to cover in lecture tomorrow. And this is actually the last section in your book. So everything, so I think On Tuesday? Wait, so tomorrow is your second to last lecture. And then Tuesday is the last lecture. Yeah, so he'll probably cover review material on Tuesday. And maybe tomorrow as well, because this doesn't take too long. All right, so nonlinear systems recall, right, that we have x prime is equal to some function of xy, y prime is some function of g of xy. But now f and g aren't just like lines. All right, they're not just ax plus by. They can be any function we want. So again, for nonlinear systems, we want to analyze behavior at equilibrium points, right? However, recall how we find equilibrium points. Equilibrium points are x and y such that f of xy is equal to g of xy is equal to 0. Okay, so firstly, we want to find our equilibrium points given a nonlinear system. The second step then is we want to find the Jacobian at these points. Okay, so what is a Jacobian matrix? So the Jacobian matrix is equal to df dx, df dy, dg dx, dg dy. Right, so you have your f and x's, f's and g's, and you plug them in, and this is what you get. Okay. So now what? So then after you find your Jacobian, right, then you find your eigenvalues and eigenvalues of Jacobian at a point. And then we want to refer to the table that we had initially. Then refer to table to characterize the equilibrium point. So not a point, but at equilibrium points. Okay, so we actually need to make one small modification to the table now. So if we go back up to the table, kind of somewhere, right? So these are the eigenvalues, these are the cases, and here's the type of equilibrium points. So we need to make sure that we distinguish that this is the linear and this is the nonlinear case. All right? And so what's the difference between the linear and nonlinear case? Well, everything is the same except for pure imaginary. Okay? So that's the same, that's the same, that's the same. Oh, pure imaginary, not the same. Complex stuff, that's all the same. All right, so if you remember for pure imaginary, for linear systems, it's a stable center. So we just literally just drew some ellipses or circles around the origin, and we were like, okay, we're good, right? And then we just determined the direction. But if you have a nonlinear system, we actually have no idea if it's going to be a center or if it's going to be a spiral. So first of all, it's going to be a center or a spiral. Okay, and then the second thing is that we actually don't know if it's stable or not. So again, this all depends on like what the heck the system is. So the stability is indeterminate. All right, so that's like the only change. Everything else, exact same thing. Find your equilibrium points, evaluate Jacobian, and whatever eigenvalues you get, there you go. Okay, so we go back here, and let's do an example. So I have x prime is equal to y, and I have y prime is equal to 4x minus x cubed minus y. So you can actually just see it on the board here. So how do I find my critical points, right? My critical points are where x prime is equal to y is equal to 0. All right. Well, that actually just right away tells me that y is equal to 0 is a necessary condition for this to be a critical point or equilibrium point. Okay, and then what's the other condition? Well, I need 4x minus x cubed minus y is equal to 0. But I already know that y has to be 0 in order to have an equilibrium point. So this must mean 4x minus x cubed is equal to 0, right? Because this is 0 already from above. Okay, and then you can factor this to find your x's, and you'll see that x is equal to 0 and then plus or minus 2. Which means I have 3 equilibrium points, or critical points, or whatever you want to call them. Negative 2, 0, 0, 0, and 2, 0. And so if you're wondering how do you find equilibrium points, if you remember back to 114, you had to take this thing called a Hessian, right? And then you had to wait, was it the Hessian? Was it the Jacobian as well? Yeah. One of the things you had to find equal to 0 to find your extrema points. You had your saddle points, you had local mins or local maxes, right? No, not the discriminant. But it's like the exact same thing. It's literally the exact same thing. You just have to find points where your derivatives are 0. Okay. So, all right. So now I got 3 equilibrium points. So now I have to evaluate this Jacobian at each one of these equilibrium points. All right. So the Jacobian is equal to, all right, df dx. So here is f. All right. So I take y and I take a partial with respect to x. Well, that's just 0. Right? And now I take y and I take a partial with respect to y. And that's going to be 1. So I put that in. All right. Now I go to g, right, and do dg dx. All right. So this one's a little non-trivial, but it's 4 minus 3x squared. And then I take dg, which is this y prime function, and I take a derivative with respect to y, and I get negative 1. Okay, so now I need to evaluate each point. So I'm going to evaluate the 0, 0 critical point first, right? So what does that mean? So anywhere in my Jacobian matrix that I see an x or an y, I plug in the point 0, 0. So 0, 1. This is 4 minus 3 times 0. It's 4. And negative 1. And now we want to find the characteristic polynomial. All right, and you'll see that you get lambda squared plus lambda minus 4 is equal to 0. And so we want to solve for this lambda, right? So lambda is equal to negative 1 plus or minus square root of 1 plus 16 over 2. And whenever you have this case, you need to be careful that the whatever's inside the square root is bigger in magnitude than the b term out in front. So, I mean, here we can see it pretty clearly that, right, negative 1 plus root 17 over 2 is going to be bigger than 0 because this guy is about 4, right? And then negative 1 minus root 17 over 2 is pretty clearly less than 0. Okay, so we have opposite sign roots. So what does that make this? This makes this a saddle point, right? Now let's take the Jacobian at 2, 0. So that's going to be 0, 1, and then 4 minus 3 times 2 squared. So 4 minus 12 is negative 8. So 0, negative 1, 0, 1, negative 8, negative 1. All right, and we get lambda squared plus lambda plus 8 equals 0. Okay, and lambda is going to be negative 1 plus or minus root 1 minus 32 over 2. So negative 1 plus or minus I root 31 over 2. Okay, so what kind of point is this? Yeah, it's going to be a spiral, and more importantly, it's going to be a stable spiral. Okay, so this is a stable spiral. All right, and now we need to find the Jacobian at 2, 0, or negative 2, 0. But what you realize is that the Jacobian at negative 2, 0 is equal to the same thing, right? Because the only point we're plugging in is essentially the x point, and we're squaring it. Right, so the Jacobian at negative 2, 0 will get you the exact same matrix, and there's no reason to go look for the eigenvalues there, because you already know them. All right, so that means that we have a saddle and we have 2 stable spirals. So how do we sketch this thing? All right, well, we do the following. So we draw our xy plane. Right, and now what are my equilibrium points? There's one out here at 2, 0. There's one at the origin, and then there's one at negative 2, 0. Okay. So now what? Now we got 2 lines, right, going through the origin, because I have a real, I have a saddle point there with real values. The eigenvalues are kind of crappy, right? Negative 1 plus or minus root 17 over 2. So we're just going to like hold off with like finding the eigenvectors for now. But in theory, you'd find the eigenvectors, right? And then you would know like which direction they're going in, right? So since it's a saddle point, what must be true about the eigenvectors? Opposite direction, right? One's pointing into the origin, one's pointing away from the origin, right? So I'll just give this one away. This one is pointing into the origin. This one's pointing away from the origin. Okay. So the one that's pointing into the origin, that's like the negative eigenvalue, right? So this is like the negative 1 minus root 17 over 2 eigenvalue because it's pointing into the origin. Okay. So now what? So now we need to characterize our equilibrium point. And so here we have, at the 2 ends, we have stable spirals, right? At the 2 ends. So we know here that there's going to be like some spiraling thing going on, right? Over there. Okay, but now what is the other behavior? Well, we have saddle points, right? So right here, what the behavior out here, it's going to be something going like this, right? Where you approach and then you go away. But what happens is if you're close enough, you start getting absorbed by the spiral, right? So you'll end up like that. All right, and the same thing's going to happen. If you come from here, you're going to, if you get close enough, right, you'll get absorbed by that spiral. Okay. So what if we're out here, right? If we're out here, well, we start coming down, right? And then we deflect away from the origin. But again, if you're close enough, you start spiraling in, right, towards that stable spiral. So your stable spiral points are kind of like black holes. They kind of just like suck you in if you're too close. All right, and the same thing over here. We're coming down, and then we try to go away, and then right, and we are sucked into the spiral. All right, yeah.
So these lines can move across the straight line.
Yeah. Because it's like because for nonlinear systems we can only look at local behavior. We can't look at global behavior, right? So we look at local behavior around the equilibrium points, and if the equilibrium point at -2, 0 just has such a strong like pull, then it will, yeah, the other eigenvector going away. Yeah. But like we do know what direction these lines are going in. Right? Just follow the eigenvector path. All right. And lastly, right, if you're like too far away, like what's going to happen is if you're too far away, you're just not going to get pulled in by that spiral, and you're actually just going to go asymptote away from to the eigenvectors. Okay? All right. Any questions? So a lot of these pictures that we're doing right now, like you might be wondering like, why the hell are we doing any of this? So one interesting application that you possibly can think of is in like evolutionary biology. So if you go back to like this system of equations here, if you think of X as like the population of species and Y as a population of another species, right? What is X prime and what is Y prime? X prime is the change in species over time, right? And Y prime is the change in species over time, right? And if you have a stable ecosystem, right, X prime and Y prime are going to be 0, right? So what is that? Well, if X prime and Y prime are 0, that means you're at an equilibrium point, right? Which means your ecosystem, right, is stable in the sense that, you know, your animals are like killing each other, but they're reproducing at the like correct rate. Okay? So then what happens if you're at like an unstable point or a stable point? So let's think about what happens if you're at an unstable point. Say you're at, I don't know, this guy up here, right? Say that this origin is a stable point, is an equilibrium, but you just get a little bit knocked out of your stability by like some like natural event, right? Natural disaster happens, like a bunch of species die randomly. So now you're at some point not on the equilibrium, right? But if it was an unstable equilibrium, what's going to happen? Well, you're going to start escaping away from that equilibrium, right? So you're actually never going to get back to like that equilibrium balance. And so like one species might go extinct or something like that, right? But if you're at like a stable spiral, right, or a stable point, right, what happens if you're knocked off your equilibrium, right? What happens is you actually go back to your original population, right? Your original long-run equilibrium population. So a lot of biologists like actually study like you can actually study evolutionary biology by using like systems of differential equations. So that's like a cool application. Again, we don't have any problems that like show you this, but this is like a pretty clear application of that. Another application that I see occasionally is in game theory, where if you think of X and Y as like strategy and payoffs, you can think of you can think of X prime and Y prime as like how many times like you're changing your strategy over time, and like an equilibrium strategy like will always get you like the same amount of like payoff or whatever. So there are a lot of applications of systems of equations, but because this is like a calculus class and not like an applied math class, we're not really going to dive into them, but just to let you know that they're out there. All right, so a few things. So next week I will be holding recitation. There's no recitation homework for next week. So what I think I'll do next week is we're going to do a review, and I'll do one of those like cheat sheet kind of reviews where I'll just try to hit like every major topic we've covered in this class in like 50 minutes. I don't know how realistic that is, but I'm going to try nevertheless. And so about the final exam, I don't know if you're allowed a cheat sheet yet because they haven't decided that. The other class does have cheat sheets. So I guess like for you guys, it doesn't really matter either way because if there's no cheat sheet on the final, like we're used to that, but the other class is not. So that's like good for you guys. And then if there is a cheat sheet on the final, then hey, we just have this other resource we can use on the final now. So either way, I don't think that matters too much for us. So no recitation homework for next week. What we might do is that we might like just over the course of like reading days and like leading up to the exam, we might just have like 1 or 2 Canvas questions like a day. It won't take you too long, but that's just to get you to like review like your old material. So that and they'll be like worth like 1 or 2 homework points. So like if you want to skip them, like it's like perfectly fine. It won't like hurt your grade like at all. But that's just to like, get you to start reviewing for the final exam. And then what else? I have exams here, so let me just pass these back right now. At least the people who are here. All right, Felix. Carolyn. Tara. Yeah. Oh, yeah. Take a donut. Oh, I said Tara. Sorry. Melina. There's Tara. Yeah. So the average on the exam, I think. Hi, Chen. Paul. The average on the exam is like a 49. Aria. No, I haven't calculated that. Oh, here you go, sorry. Yeah, so the average was 49. The median was also a 49. So, Leah. Kara. Michelle. Ian. Yep. Anyone not get their exam? I think I got everyone there. Yeah, so overall we were pretty happy with how the exam turned out. One thing that I do want to say is that if you ever have a question with the matrix and you need to find the eigenvalues and eigenvectors of the matrix, like spend your time to find the correct eigenvalues and eigenvectors, because that's like the brunt of the work. Because like it's impossible to grade like wrong eigenvalues. Like I don't know, like I think I've said that before, but it's like if you have the wrong eigenvalues, it's just like I'm not looking at anything meaningful here, so I'm just not going to look at it. So just keep that in mind when you're studying for the exam or like on the final. All right, and then if you have any questions, let me know. I have office hours today from 1 to 2 p.m.